Have you ever wondered how all the intricacies of our universe fit together? From the smallest particles to the grandest cosmic structures, the universe is a complex tapestry woven from a diverse array of elements. In our quest to understand this cosmic tapestry, we've identified four fundamental forces that govern everything. First, we have gravity. This force, described by Einstein's general theory of relativity, is the maestro conducting the cosmic orchestra. It governs the motion of planets, stars, and galaxies, holding the universe together. Second, there's electromagnetism. This force, encapsulated by quantum electrodynamics, deals with the phenomena of electricity and magnetism. It's the force that lights up our cities and powers our technology. Then we have the weak nuclear force. Explained by the electroweak theory, this force is responsible for certain types of radioactive decay in atomic nuclei. Lastly, we encounter the strong nuclear force. Described by quantum chromodynamics, it binds quarks together to form protons, neutrons, and other particles. While each force works perfectly within its own realm, the challenge has been to unite them under a single theoretical umbrella. This is where the theory of everything steps in. It's a theoretical framework that seeks to reconcile all these forces into one comprehensive theory. Imagine a jigsaw puzzle. Each force is a piece of that puzzle, fitting perfectly within its own space. But when we attempt to put all the pieces together, we find that they don't fit as neatly as we'd like. That's the dilemma we face in physics today. The theory of everything is our attempt to find a picture where all the pieces fit together seamlessly. It represents our quest to understand the universe at its most fundamental level and to decode the very blueprint of existence. The journey to the theory of everything is a voyage into the heart of the cosmos, an attempt to decode the universe's fundamental blueprint. It's an adventure that takes us from the tiniest particles to the vast expanses of the cosmos as we strive to unlock the profound mysteries of the universe. Let's turn the clock back to the time of Albert Einstein, a time when our understanding of the universe was about to be revolutionized. Einstein, a name synonymous with genius, introduced us to a new perspective on gravity. His general theory of relativity painted a picture of gravity not as a force but as the curvature of space-time itself, caused by mass. It was a brilliant, beautiful theory, and it worked wonders on a cosmic scale, accurately predicting the motion of planets, the bending of light, and even the expansion of the universe. But as we began to delve deeper into the fabric of reality, down to the scale of atoms and subatomic particles, we found that Einstein's theory couldn't follow us there. The principles of general relativity, built on the predictable laws of classical physics, clashed with the probabilistic, uncertain nature of quantum mechanics. Gravity, so elegantly explained by Einstein on large scales, seemed to vanish when we tried to apply his theory to the quantum world. This disconnect between the macro and micro realms of our universe presented a puzzle that perplexed even Einstein himself. He spent the latter part of his life searching for a way to unite his theory with the strange world of quantum mechanics, but to no avail. His dream of a unified theory remained unfulfilled, a tantalizingly incomplete masterpiece. But don't mistake this for a failure. Einstein's theory was a groundbreaking stride in our understanding of the universe. It laid the groundwork for modern cosmology and paved the way for the discovery of black holes and gravitational waves. It's just that the symphony of the universe as described by Einstein was left with a few missing notes. Einstein's theory was a leap forward, but it left us with an unfinished symphony, a universe divided. The quest to complete this symphony, to find a theory that can describe the universe in its entirety, from the largest galaxies to the smallest particles, continues to this day. And that's where we'll pick up in the next scene, as we delve into the fascinating world of quantum mechanics. In the microscopic world, a different set of rules apply. Here, we're not dealing with stars, galaxies, or even atoms. We're venturing into the realm of subatomic particles, where quantum mechanics reigns supreme. Quantum mechanics is a branch of physics that describes the behavior of particles at the tiniest scales. It's a world where particles can exist in multiple places at once, pop in and out of existence, and even teleport through barriers. These are not the ordinary rules of the universe we're familiar with. but they are the laws that govern the quantum world. This theory has been incredibly successful in explaining the strange phenomena we observe at these small scales. It's the foundation for much of modern technology, from computers to lasers, even the GPS system in your smartphone. Quantum mechanics has shown us a world far removed from our everyday experiences and has reshaped our understanding of reality. However, as triumphant as quantum mechanics has been in explaining the small, it's been equally unsuccessful at incorporating gravity, the force that shapes the universe on the largest scales. You see, gravity, as described by Einstein's general relativity, is a smooth, continuous force bending the fabric of space and time. But in quantum mechanics, forces are carried by particles, and these particles are inherently discrete or quantized. This fundamental distinction between the continuous nature of relativity and the quantized nature of quantum mechanics has been a significant roadblock in our pursuit of a unified theory. Quantum mechanics, with all its quirks, provides an incredible description of the universe on the smallest scales. Still, it falls short when trying to bridge the gap to the cosmos. So, we're left with a puzzle. Two incredibly successful theories, each describing different ends of the universe, yet seemingly incompatible. This is the quantum puzzle that scientists have been grappling with for the better part of a century. Quantum mechanics opened a new window into the universe, but it couldn't bridge the gap to the cosmos. Our quest for a unified theory, a theory of everything, continues. The quest for the theory of everything is a journey to bridge this cosmic divide. It's a journey that has seen brilliant minds grapple with the complexities of the universe in an attempt to reconcile the seemingly irreconcilable: quantum mechanics and general relativity. Imagine trying to combine a symphony and a rock concert. Both are music, but they operate on different principles, follow different rules. That's the challenge physicists face when trying to reconcile quantum mechanics, the symphony of the subatomic world, with general relativity, the rock concert of the cosmos. The goal? To find a unified theory that can describe everything from the dance of galaxies to the jitter of quarks. The hope is that such a theory would provide a consistent description of the universe, from the smallest quantum particles to the largest cosmic structures. Enter string theory, one of the most promising candidates for the theory of everything. This theory proposes that, at the most fundamental level, everything is composed of tiny, vibrating strings rather than point-like particles. It's like replacing the individual musicians in our symphony and rock concert with a single universal instrument, a vibrating string. String theory attempts to reconcile quantum mechanics and gravity, promising a unified understanding of all forces. It's a vibrant new melody, a tantalizing glimpse of a cosmic symphony where every note, from the tiniest particle to the grandest galaxy, is part of a harmonious whole. But like any grand endeavor, it's not without its challenges. String theory is still in its infancy, and much of it remains to be tested. It's a symphony yet to be fully composed, a rock concert yet to be fully staged. String theory holds the promise of a unified universe, but it's a promise yet to be fulfilled. As we continue our quest for the theory of everything, we embrace the uncertainty, the unknown, and the unexplored, for they are the melodies that make up the symphony of science. The road to the theory of everything is fraught with challenges. String theory, despite its promising features, still has mountains to climb. For one, it requires the existence of extra dimensions beyond the three spatial and one temporal dimension we're familiar with. This is a radical departure from our everyday experience and poses a significant challenge for experimental verification. Moreover, string theory, in its current form, does not predict a unique solution. Instead, it allows for an almost infinite landscape of possible universes, each with different physical constants and laws. This multiverse interpretation is philosophically intriguing, but makes it difficult to pin down a definitive, testable prediction. But let's not forget the other candidates vying for the title of the theory of everything. Loop quantum gravity, for instance, also aims to merge quantum mechanics and general relativity. However, it too faces its own set of challenges, such as the difficulty of incorporating the other fundamental forces beyond gravity. These challenges, while daunting, are not insurmountable. The quest for the theory of everything is an ongoing journey, filled with obstacles, yes, but also with tantalizing possibilities. Imagine the implications of a successful theory of everything. It would revolutionize our understanding of the cosmos, providing a complete, consistent, and unified picture of the universe. It could answer profound questions about the nature of space and time, the origin of the universe, and the fundamental constituents of matter. Such a theory could also have far-reaching implications beyond physics, impacting fields like cosmology, philosophy, and perhaps even our perception of reality itself. The theory of everything remains elusive, but the journey itself continues to push the boundaries of our understanding and inch us closer to the cosmic truth. As we strive to weave together the disparate threads of fundamental physics into a harmonious cosmic symphony, let's remember, it's not just about the destination, but also about the voyage of discovery along the way.